Okay, so let's start. We'll continue with the yes. So peer evaluation. So any one from group 101?
Me. No, thank you.
102? No, this is the actually this is peer evaluation. So it's another group's report. Yeah. 103? 104? I'm sorry. 104, right? 105? 106? 109? Yeah. 107? 8? 11? 12? Which number? 114? Oh, 111? Yeah. Okay, so and also I just sent an email that I put some lecture notes that are more detailed than you have in the another state machine one. It's a different one. So I added a column as detailed notes with the notes that are contain essentially more information. So you can use it for your review for the final exam, but keep in mind that only what I discussed in class will be covered in the final exam. So okay, so we'll continue with the black box testing. So black box testing is we'll test without access to the source code. Say you get an exe file only from someone. The tester may not need to understand the source code. You just get the executable file from the developer and the input-output specifications, and then just test the functionality of the system without caring about what's inside of the system. So attempts to find incorrect or missing functions, essentially the functionality of the system, not the internal control and data flow behavior like in the white box testing. So to achieve reasonable testing, you should cover a range of input-output values because errors often happen at the boundaries of your input ranges. So you should pay special attention to the boundary conditions. So equivalence partitioning partitions the inputs into a set of different partitions, and you should pay special attention to the boundaries of the partitions. So here's if the input is a range, here are some guidelines for selecting equivalence classes. If the input is a range, say if the range is this valid range is here, say 0 to 5,000. Then anything less than 0 or greater than 5,000 will be out of the range. So you should pick some valid values from the in-range partition equivalence class, and some values from the less than range and some values from greater than range, and see how the system responds. Right? So the system should respond saying that the value is out of range. That's the correct response. but it shouldn't crash or return you some garbage value. So if the input is a specific value, then you pick one valid, which is the this value right here, and two invalid equivalence classes, less than value and greater than value. So at testing time, you pick one value from each of the three equivalence classes. If the input is the self-related values, then you have two equivalence classes, also called partitions, member of a set or not member of a set. So a member of a set is the invalid class, and not member of a set is an invalid class. And if the input is a Boolean variable, then you have one valid that is a Boolean value, and one invalid equivalence class, which is a non-Boolean value, that is floating point or integer. So more errors occur at the boundary than in the center. So you should pick values to first you pick typical values inside an equivalence class, and then you select values at the boundaries of an equivalence class, both within the valid range and in the invalid range. So if the input is a range and is bounded by A and B as the lower and upper bounds, then use A, B, and values just below and just above A and B. So input is a range with the minimum value A, maximum value B. So suppose it's an integer range, then you try A minus 1, A plus 1, B minus 1, B plus 1. If it happens to be a floating point range, perhaps you specify some user-defined delta, say 0.05 and A minus 0.05 or A plus 0.05. So if the input is a set of discrete values, then use the minimum and maximum of the values, and the values just above and just below them. So say input is perhaps 0, say 50, say 200, and perhaps this is 260. Then you take the minimum and try the one just below it, that is minus 1, and just above it, that is 1, even though these are not valid inputs. So, and also take the max and to try the one just above and just below it. So this is also applicable to a single input, specific input value. If the input is a set of values, then you test all values in the set, if possible. That is, if the set is relatively small. Otherwise, if the set is too large, you sample a few values and one value outside of the set. So the special case is if the input is a Boolean, then the set has two values, true or false, and you pick a value in the non-Boolean set, which could be an integer, could be any garbage value, and see how the system responds. So typically, if you're writing code, if you pass in a input as not a Boolean for a function that takes a Boolean as a parameter, the type checker of the compiler will catch it. But here we're really testing the system as a black box. That is, you have a user interface, you're inputting some garbage value. The best approach is to catch it in the UI. Just don't allow you to input a integer when you're expecting a Boolean. If the UI doesn't catch it, your underlying code should respond with an error message if you pass in a non-Boolean value. And apply guidelines 1 and 2 to create output values at the minimum and maximum expected values. So guidelines 1 and 2, that is, input is a range or a set of discrete values. Substitute the word input for output. And then try to design inputs to force your outputs to be at either just above or just below the minimum and the maximum ranges. So if the output is a table, then create a minimum size table and a maximum size table as defined in your problem. So create output values at their minimum and maximum expected values. So in this case, it's perhaps not possible to create output values at the minimum -1 or maximum +1. So that's the difference between creating output values versus input values. Just apply guidelines 1 and 2, except you only create valid outputs. So if data structures have boundaries, test the boundary values and just values just above and just below them. So if the array with bounds 1 to 10, then test array index 0, 1, 2, based on our principle of testing the boundary values, and 9, 10, 11. So because array out of bounds error is a very typical programming error, so you need to test for those. Notice that this is really different from the first guideline 1, which says the input, you take the values as boundaries. The data structures can be any data structure used within the system, not just for the inputs. So it's a really more pervasive requirement of testing all the internal data structures. Whenever you see a data structure with an array with bounds, then you try to try the boundary values at the bounds. So here's one example of student record search. So maintain student information use case uses a procedure that searches the database for the record of a given student. Input to the search procedure is the student ID. Output is either a success indication and the student record is containing the given student ID, or a failure indication, and a message indicating the nature of the failure. That is, the nature of the failure could be the ID is in the valid range, but it's not found. It's not a valid ID. There's no student with the ID. Or the input ID is simply out of range. So the valid range is from 1 million to 1 less than 10 million. So for the typical test categories, following test categories, typical values, boundary values, and other, that is invalid values, what specific test values and test cases should be used to test whether the search procedure works correctly and accepts only valid student IDs. So this is clearly a range. And it's a large range. You should not treat it as a set. You can view it as a set with 10 million members, but it's more appropriate to view it as a range. So test cases, you have first two, mid-range, valid student ID, either existing or non-existent student record. So you take the one valid in the middle, say 5 million, which corresponds to an existing student record, and 5,000,001, which corresponds to a non-existent student record. Even though the ID is a valid ID, it's in the range of 1 million to 1 less than 10 million. Below lower range, that is to take the 500,000, which obviously is outside of the valid range, and 15 million, which is above the upper range. So that's the typical values based on the range equivalence classes. So you pick two values from the valid range and one below and one above. And then boundary values, we take the minimum range 1 million and try the one plus 1 and minus 1. And then we take the maximum range and try the value of plus 1 and minus 1 based on the guidelines for testing boundary values for the range-based inputs. And finally, you pick feed in a garbage value that is just not valid, say 5647 ABC, which is not a numeric value. So the best way to design your system is, of course, to do validation at the UI level and not allow you to input any non-numeric characters at all. But if you do it at the later stage and allow you to enter it, and then when you click a button, it gives you an error. That's fine too. So the black box tester doesn't care how you implement the system. So as long as the system responds with the correct error messages when you get the invalid inputs, it passes the black box testing. So that's the test inputs. Then the test cases are the actual procedures for doing the testing. So you have a test case name called mid-range dash valid student ID existing student record, and the setup to ensure that the record with student ID 5 million exists in the database. Test value is 5 million. Verification is successful retrieval of student's record with ID 5 million. So a typical test case is just like that. You have how do you set it up as the really the test precondition, and you pass in a value, and you verify if the test passes or fails. And for each of the input values, you write a test case. 5,000,001 is a non-existent student record, and verification success is when you do an unsuccessful retrieval and no such record error message. If you get such an error message, you pass the test. And if you get a below lower range value, 500,000, then the verification is invalid student ID error message. So you should give the correct error message for the two types of errors. One is valid ID but no such record. One is invalid ID. And also you have above upper range invalid student ID error message. And for the boundary values, you have the 6 cases we discussed. You have 1 million successful retrieval should be the verification condition. Well, 1 million plus 1 successful retrieval. Notice here the setup is to ensure that a record with the student ID 1,000,001 exists in the database. And you pass in 1 less than 1 million, you get an invalid student ID error message. And similarly for the upper bound boundary values. So, no questions? So again, the reason you do the boundary testing in addition to the typical value testing is that errors are likely to occur at the boundaries. Perhaps the programmer mistyped a greater than as greater than or equal to. It's very common to make that kind of typo mistakes. So this kind of boundary testing will catch it. So validate rating is the procedure in the video sales example. Is to validate the review rating input by the user. Check to see that it's an integer value from 1 to 5. So you try typical, boundary, and other test categories. So input is 1 to 5, so you can treat it as a range or as a set. This only 5 values, so it's small enough to treat it as a set. Or for the previous one has 10 million values, so it's too large to be treated as a set. So in this case, we can treat them as a set of values and test all of them. However, if the input, since the input values are also integers, we should also apply the test for a range of values. Of course, if it's a floating point range from 1 to 5, then you can only treat it as a range. So we choose to do both and use the following test cases and values. So test case 1, set member slash in range. So that is 1, 2, 3, 4, 5. You enumerate all the members in the set. Remember, when we test the set, we say enumerate, try all the possible values if possible. Here it is possible. Below range, pick a -5, or you can pick a -10. It doesn't matter. Or not. Above range is 9. So that's the typical values. And for the boundary values, you try the cases. Remember, for the boundary values we said you try the lower bound ±1, upper bound ±1. So here 1 ±1 is 0 and 2. 2 is already covered by the exhaustive testing of all the set members. So just list 0 here. Similarly, you have 5 ±1 is 4 and 6. 4 is already covered. So you just cover 6 here. Other values, that is, you pass in invalid inputs like 2.5, like a character P instead of a numeric value, or like a null input as an invalid rating. So obviously, if you have the better design for the system is to have a drop box, selection box with 5 choices, 1 to 5. Then it's not possible at all to pass in any non-valid inputs, and all these invalid ratings and below and above range automatically these tests will automatically be satisfied. So a good design practice is to catch the error as early as possible and try to propagate only valid inputs from the graphical user interface down to the lower level of the code. So another type of testing is threat testing. That is an event-based approach where tests are based on events which trigger system actions, particularly appropriate for object-oriented systems. We have a picture in here. So you have a bunch of objects, and they pass messages and back and forth. So object 1 has input 1, 2, 3, three kinds of input events, and say object 3 gets an input and produces an output. to object 2, which produces an output to object 4, which produces output to the outside. So this is a thread. You can think of the object as passive, sitting there, a thread as the active entity, invoking the methods of the objects. So you can imagine a thread as meandering through the maze of objects, invoking different objects' methods, and eventually finish with final output. So you have types of thread tests you should conduct include single thread, where you pass in the input 1 and observe the system behavior that happens while the events propagate through the system to the output. And multi-thread, where a thread forks off 2 branches. From object 2, you go off to object 4 and 5. Say this is typically done with operating system calls to create new threads. And multi-input thread into object 1, where all the 3 inputs must be present to trigger object 1. Object 1 reads all the 3 values before it does its internal computation. And of course, the verification conditions are not specified here. You should essentially compare the output values from the very end of the threads, and also check for any possible deadlocks, mutual exclusion conditions. So let's go back to the first slide. So it's particularly appropriate for object-oriented systems because the objects pass messages around. It's a very natural paradigm. And it's after classes have been unit tested and integrated into subsystems. That is, each individual classes, after you've done the black box testing with all the input ranges, is being tested to be correct. And then you're testing the integration of all the objects together. Needs to identify and execute each possible processing thread by examining the use cases. So typically a thread corresponds to a particular use case. So may not be possible to do a complete thread testing because there may be too many input-output combinations in terms of the program execution path through the system. So we should focus on the most commonly exercised threads, that is, corresponds to the basic flows through the flow of events. So remember, the basic flows are the most commonly run scenarios, while the alternative flows are less commonly exercised. So if it's not feasible to test all of them, then just focus on the basic flows. Focus on the common case. So in that way, if the uncommon case has bugs, then the bugs only happen rarely, so perhaps it's not such a big deal. So another type of testing is state-based testing, where you compare the resulting state of a class with the expected state. So this is typically derived test cases using state machine diagram for a class. Derive a representative set of stimuli, that is, events for each transition, similar to equivalence testing. That is, you look at the state machine and look at each state what events are valid. Remember, not all events are valid. Some events may be ignored in certain states. So if you pass in those events, the system will not respond. So check the attributes or links of the class after applying a stimuli to determine if the specified state has been reached. Remember, a state is typically defined by the values of the attributes or links to other objects. For example, for a bank account object, you're in the imbalanced state if your balance attribute is greater than 0, and you're in non-imbalanced state if it's less than 0. And if a rental copy has a link to a customer, then it is it's in the not available rented state. Otherwise, it's in the available state. So by checking the attributes and links, you can determine which state the object is in. So you first need to put the class in the desired state before applying the stimuli. That is, you're trying to drive the system from state 1 to state 5, for example. While the initial state is in state 0, but to drive it from state 0 to state 1, you may have to jump over many different intermediate states. And it may not be very easy. So this is maybe a little confusing that it's black box testing, but it requires knowledge of the system state machine. But it does not require knowledge of the source code. So the state machine could be part of the class documentation, and you can use it to derive your test cases. But you don't have access to the source code to do the control flow testing. So now we're done with the design tests. We go to implement tests. So the implement test is to automate the test procedures as much as possible. Because running test cases can be very tedious and time-consuming. There are many possible input values and output and system states to test. So a test component is a program that automates one or several test procedures or parts of them. So there are tools available to help write test components that record the actions for a test case as the user performs the actions and parameterize the recorded scripts to achieve a variety of input values. So never mind, we'll pick it up. So a test component is also called a test driver. So essentially, this is something. So imagine you have to try 5,000 input values. Obviously, if you write all the test cases by hand, it's going to take you a while. But with these automated tools to help you, you can for example, you can perform some tests, and these tools record the actions from the GUI, and then automatically derive the test scripts based on your actions. This is especially beneficial for GUI testing. So instead of manually writing the test script as clicking button 1, input value 2, clicking button 2, etc., which could be very long, you can the test components sit in the background and watches your actions. And we are done with one test. It'll generate a bunch of different test scripts for you, so you can run them automatically in the future. Spreadsheets and/or databases can be used to store the required input data and results of each test. So you achieve a high degree of automation. Instead of watching the output on the screen and jotting down the result by hand, you directly feed them into a spreadsheet or database and do some statistical analysis later. So then we distinguish between unit test, system tests, and integration tests. So to perform tests, you take as input the software configuration and test configuration. Software configuration includes the requirements analysis and design, the 3 documents, and source code, which are used for white box testing but not for black box testing. Test configuration includes test cases, test procedures, testing tools, and expected results. And you run the tests and put the results in the database and do evaluation. Based on the expected results, comparing the test results with the expected results. And if you detect no errors, then you're done. The tests have passed. If you detect errors, then you pass it to the development team and debug the errors. And after the corrections are placed into the source code control system, you redo the tests. And finally, you collect error statistics to update the reliability and quality model. So this is the thing to tell you the trend of the bug rate. And if you see a continuously falling trend, you can perhaps interpolate the reliability of the software and then decide if it's worthwhile to do more tests, or you have reached the region of diminishing returns, and doing more tests won't help you much, and then you should perhaps stop. Remember, it's not possible to exhaustively test all possible behavior. You must make a decision and accept the fact that your software will have bugs in it. And it's okay as long as the reliability is acceptable. So a testing strategy specifies which testing techniques, white box, black box, or thread-based testing, and also state-based testing are appropriate for at which point in time. So it integrates test cases into a well-planned series of steps that test a component/subsystem by specifying what are the steps that need to be conducted to test a component. Perhaps you try the white box testing first and then followed by black box testing. What are the steps planned and undertaken? And undertaken is the stuff you have done before, and planned is the stuff you will do in the future. How much effort, time, and resources will be required to do the steps? Resources include monetary and human resources. So test planning is difficult due to time uncertainty in the debug part. So some bugs are very easy to fix. Some bugs may take you a few days or weeks to fix. So the planning may be hard. So a testing strategy needs to balance flexibility and creativity with planning and management. It should leave enough flexibility in the system so that you don't run into problems near deadlines. So testing often occurs when deadline pressures are most severe. That is, testing. The most amount of testing is done, especially the integration testing, at the very end of the project, near the deadlines. So, therefore, progress must be measurable and problems identified as early as possible. So, by measurable, we mean that you you should have a sense of how much testing you have done and how much more needs to be done, instead of just have a big bang testing approach without any idea of how much testing needs to be done in the future. So try to identify problems early. That is, try to do testing as you doing developing, instead of leaving all the testing to the end. So one testing strategy. So is this? So this is looks a little bit like spiral process, but it's different. It's a testing strategy. So you are going from the outside to the inside, developing the system from the outside to the inside, from the requirements to analysis to design to the implementation, but you're testing from the inside to the outside. So unit testing, that is, you're testing each small components as you develop these components. Integration testing, you're testing integration of multiple components into subsystems. And system testing, and finally acceptance testing by the client. So acceptance testing really is testing the requirements. So it corresponds to the requirements capture. Unit testing corresponds to the coding part. And roughly integration testing and system testing are done corresponds to the design and analysis. So this correspondence is a little loose. So, but it's the basic idea. So, so you are doing testing from the most concrete, most detailed parts up to the most abstract level. So who should do the testing? So that's the question. So acceptance testing is obviously done by the client as part of the contract. Unit testing and integration testing, you can do it. The developers or testers can do it. So you need to make a decision. Do I have a slide here? Let me see. Yeah, so there's a hidden slide here. So unit testing is typically done with white box testing, done by the component engineer who developed the code, verifies that each component and subsystem functions correctly. Integration testing can be done with black box and white box testing, a combination of both. Perhaps for some parts use white box and some parts with black box. So done by the component engineer and or independent test group as integration system testers. And system testing is done by the independent testing group. So with black box testing. So finally, acceptance testing is done by the client user. So this is one testing strategy. Obviously, you can have other strategies. If your company is too small, you can let the developers do all the testing. Notice that you're doing unit testing by the developers as they're developing the components. This is especially the case for the so-called extreme programming, which we talked about before, so-called test-driven development. That is, you're writing the test cases for the components as you're developing the components at the same time. So when the component development is done, you have the source code, then you run the test immediately to catch errors early. So, perform unit testing. So, unit testing is when you test each individual component. So you have designed a bunch of test cases. Here we use this shape to show that you may have many test cases for different possible inputs. So you may have different type of test cases. Those may be testing boundary conditions. Some may be testing data structures, like array out of bounds errors. Some may be testing error handling paths, try to force the system into exceptions. Some may be testing independent paths, like the basis path testing we discussed before. Some may be testing the user interface. So you may have different type of test cases, and you're testing the component by providing different inputs. Unit testing is mainly white box testing. So a driver is a component that calls the component to be tested. And a stub is a component called by the component to be tested. So drivers and stubs may need to be developed for each unit test. So because, say, a component A calls 20 other components during its operation. So if you wait for all the 20 components to be developed before testing component A, then you may wait a long time. Instead, you write a stub to provide really empty implementations for any of the functions called within the component. Because your focus is on testing the component, you can write empty stubs to replace any of the other unavailable components. And you should also write drivers, that is, other components may call this component under testing. So while the other components are not ready yet, you write a driver that is a main to stimulate the components with different inputs. So drivers and stubs allow you to test a component independent of any other component that depends on the component or the component depends on. So for object-oriented testing, the unit test has to be at least a class. But object state makes testing difficult. That is, if the object has an internal state machine. So a class needs to be tested in every state it can ever reach using state-based testing. That is, object-oriented systems are special due to their inheritance behavior. That is, testing each method in isolation might cause missed defects caused by other method changing the object state to something that exposes a defect in another method. That is, all the methods of a class may call each other, and so their behavior may be dependent on the object's state, that is the attribute values. So just testing a method with one particular set of attribute values, even though you tried all the ranges, like in the black box testing, all the valid invalid ranges, because of the internal object states may be different, it's not guaranteed to be correct in any other state. Therefore, you need to drive the object to a certain state and then test the object in every state. So how to deal with encapsulation? So in OO systems, you have private public attributes and operations. So private attributes are not accessible, so you cannot read it from outside. So you need to provide a method for testing only, that reports all of the object state. Perhaps a print all statement to print all the objects' private attributes. But you should delete the method in the production system because it violates encapsulation. How to do inheritance and polymorphism? So if a subclass overrides methods of a already tested superclass, do you only test the overridden methods, or do you test all the methods? So all of the subclasses methods need to be tested again due to dynamic binding and substitutability. So this is particular to the old system. So think of, let's have an example where you have an object, perhaps with two methods, M1 and M2, and you have a subclass with redefines M1. So the M2 is not redefined. So when you redefine M1, if you only test M1, it may not be enough. That is, if M2 calls M1 in its implementation, and if you change M1 here, even though M2 in the subclass is not changed, it inherits the code from the superclass, from the base class, which calls the subclasses M1. So you need to test both M1 and M2 if you change M1. So any questions? This is due to the inheritance mechanism. So integration testing. So if each component, every component works individually, so why do you do more testing? So interaction errors cannot be uncovered by unit testing only. So for example, the interface misuse, interface misunderstanding between different components, timing errors that only happen when you integrate components together, because the timing behavior is often end-to-end, from input to output, which may cut across many components. So here's an example from an FYP project where you had a bunch of client applications. So two client parts were implemented as separate modules, and it was required to integrate them in order to complete the implementation of the client application. A lot of errors occurred while integrating the two modules, and it was very difficult to debug the integration problem, as two of the group members who implemented the separate modules were not familiar with the other module. A long period of time was used to study both modules. Finally, it was found that both modules had different defined hardware devices which could not coexist with each other, which resulted in a lot of errors. So therefore, these kind of errors are not detectable when you are doing testing of each component alone. So integration approaches. One is the Big Bang integration. That is, so you have a team of, say, 5 members. Everyone goes off and implements something, and 5 days before the deadline, you do the integration. That's Big Bang, and that's very bad. So you should try to do incremental construction, incremental builds. That is, you're constructing and testing the system in small increments, and you're building perhaps, even if not daily, perhaps every week, to make sure that nothing has been broken by the week's development. And you do regression testing often. That is, you run old tests to make sure that what has worked before is not broken by the new developments. So this way you avoid the disaster scenario where at the very end you discover errors. So integration testing, you can do it top-down or bottom-up. Top-down is when you start with the graphical user interface, and you while you're doing the GUI testing, you write every other module at the stop, so everything is empty except the UI. So when you click a button, you say button clicked. You don't do anything. And gradually you replace the stops one at a time by either depth first or breadth first approach. Depth first is when you go down one tree branch and implement a piece of functionality from end to end. Breadth first replacement is when you are doing it one layer at a time until the perhaps the database layer. So as new subsystems are integrated, some subset of previous tests is rerun as regression testing to make sure that nothing old has been broken. So early testing and error detection of user interface components, because you're starting with the UI, and you can demonstrate a complete function of the system early, especially to gather user feedback during the requirement stage. Cannot do significant low-level processing until later in the testing. Need to write and test stops that may be very complicated. That is, your high-level components may call many lower-level components, and you need to write many stubs. And also, you don't get to the low-level processing, like the database processing or low-level networking layer, etc., until later, very late in the project. So it's usually not appropriate for all development, except to test operations of classes. So for all development, you typically adopt a bottom-up approach, where you're building the subsystems from the bottom up by writing drivers. So say you're building the S3, S4, and S5 into a single subsystem, and you need to test it. While the earlier top layers haven't been developed, so you need to write a driver for it as the main that invokes the subsystem, and you replace the drivers one at a time in a depth-first manner. So until you get to the very top, that is the graphical user interface. So the pros are that the interaction faults are more easily found, and easier test case design, and no need for writing stubs. But you do need to write the drivers. And the cons are that the user interface components are tested last. So therefore, you don't have early feedback from the user by having a complete UI available to them. So, and the system as a whole does not exist until the very last subsystem is added. Therefore, you don't have a high-level overview of the system early in the project. So it's appropriate for all development where as you're developing the classes, you're writing test drivers for the classes. Each class typically has attached for it a driver, and as you're developing from bottom up, you gradually write the other classes to replace the drivers. So both top down and bottom up have their pros and cons, and the sandwich approach is when you combine these two, where you test the subsystems with stubs as we did with top down, and you test the lower level subsystems with drivers as we did for bottom up. But you do both simultaneously, and you meet in the middle. And when you meet, you replace the bottom lower level subsystems driver with the top level subsystem, and you replace the top level subsystem stub with the lower level subsystem. And to do the complete system testing. So the pro is that you can do parallel testing. That is, you're doing top down and bottom up simultaneously, perhaps by different testers. The con is that you may need many drivers and stubs. So in top down you only need stubs, in bottom up you only need drivers, but here you need both drivers and stubs. But you can significantly shorten the total testing time because of the concurrent parallel testing you're doing. So critical subsystems should be tested as early as possible to detect any critical failures of the system. So critical subsystems are those that have high risk, address several software requirements, that is, they implement several use cases. So remember, use cases may be implemented by subsystems, while several use cases may all use a common subsystem. Especially, say, the global utility components that's used by everyone else. So has high level of control. What does this mean? Control complexity, cyclomatic complexity, indicating the control flow complexity. How many if then else? How many while loops do you have? Do you have very complex spaghetti code kind of control, or do you have very simple straight line control? So if you have a high level of control, cyclomatic complexity is high, then it indicates high chance of error. Are complex or error prone, this is related to the high level of control and have specific performance requirements, especially for real-time applications. Say for automotive or avionics applications, if your performance is not good, you may cause a crash of the system. But for desktop applications, perhaps the performance requirements are less strict. So regression testing is required for critical subsystems. While it's always a good idea to run regression testing, it is a hard requirement for the critical subsystems. So we discussed perform unit test and integration test. So now we discuss system testing. That is, the whole system has been implemented and it's done. Now you're testing the entire system to be sure that the system functions properly when integrated. So specific types of system tests. One is functional, that is, the developers verify that all user functions work as specified in the system requirement specification. What is performance? So the developers verify that the system goals are met, that is non-functional requirements like throughput or latency and scalability, such kind of requirements. And pilot testing is when a selected group of end users verifies common functionality in the target environment. So the keyword is a group of end users and target environment. Perhaps you're developing a mobile game application on your desktop, and then that's not a target environment, that's a development environment. The target environment is a handheld device. And then perhaps you give the software to a group of students who have the and also the device to the students to use them for say 2 months, and then let them play with the device and see if they see any crashes or other behaviors. Acceptance testing is when the client user verifies usability and validates functional and non-functional requirements against the system requirement specification. So here the client/user. So this is the guy who pays you. Installation is when the client user verifies usability and validates functional and non-functional requirements in the real use. That is after the system is deployed, and you observe it at the installation site. So we elaborate on the middle three in the next slides. Performance testing, you can do stress testing, that is verify that the system can continue functioning even when confronted with many simultaneous requests. How high can we go, and do we feel software collapse? So fail soft means that you fail, but it's a soft failure. That is perhaps you have a long response time, but you don't crash. So there's an interesting story that on September 11th, 2001, when the terrorists attacked all the news websites like CNN and ABC News, they all essentially crashed under many simultaneous requests of users who want the latest news. So what they did is that they put up a text version of the news, just a single text file on the website, so that they can reduce the workload of the system. So that's an example of a collapse under heavy load. So volume is to verify that the system can handle large amounts of data, high complexity, algorithms for high disk fragmentation. So this is especially true for data-intensive applications. For example, Walmart collects customer data at checkout to do a statistical analysis of the customer behavior. That data runs into terabytes per hour, so it's extremely high volume data. Imagine how many customers buy stuff every day at Walmart, and everything is recorded in the database. So you should verify the system can handle that kind of data. Security is to verify that access protection mechanisms work, make penetration cost more than value of entry. So this is obviously different systems have different security requirements. For a say online discussion forum, pretty much if you have penetration, it's not a big deal. But for a financial website with bank accounts and transactions, then you need to provide more security. So typically security is based on a username password pair. But banks have come up with mechanisms to have higher security than that. They give you sometimes it's called a dynamic password token, where you have a one-time password based on the token. If you don't have the token, you cannot log in. So timing is when verify the system meets timing constraints for real-time and embedded systems. So as I said, for avionics and automotive systems, if you don't meet timing requirements, your system may have critical failures. So recovery verify that the system, when forced to fail, can recover in various when it fails in various ways, especially database recovery. So what happens if you pull the power plug? And do you have a correct database? And if you do, how do you recover that? So pilot testing, it's a testing in a controlled environment. You have two types, alpha and beta testing. Alpha test is when you are testing it at the developer site, where the users are doing the testing. Remember, pilot testing is always done by the end users, but alpha test is when the client sits at the developer site and tests the users, so the developers can observe the users. Beta testing is when you do testing in a real environment, so that bugs are uncovered from regular usage patterns. So this is testing at the client side, not having a developer at your shoulders to watch you. So this is especially common for open source projects, where you often pull up a beta version of the new developments and gather statistics from real usage patterns, and when you fix most of the bugs, you pull up a official release. So that is done in a real environment. That is, the users actually download the software to their own desktops and use it in the field. Well, for alpha test, it's more appropriate for contract development, where the client is a specific company, and you can invite them to come to the developer site. Acceptance testing is the process of ensuring that the software meets the user's reasonable expectations based on the requirements. So it can be subjective. Therefore, good requirements specification from the start are very important, so that you can have objective criteria against which a test can be evaluated to avoid any disputes later at the end. So the method of defect resolution should be negotiated before the transition phase. That is essentially, if you find bugs and fix them, who covers the cost, and etc. So acceptance test is a black box approach covering system aspects such as functionality, performance, documentation, reliability, etc. So the result of each test is a deficiency list. That is the bug list, if any. It's a black box testing because the clients don't care about your source code. They only care about if your software can do what I asked you to implement. Right? For your system, the TAs never read your source code. They just care about functionalities. And also for your project, we don't do performance testing. So we only do functionality testing. So configuration review is an audit that ensures that all elements of the software delivered to the client, software configuration, have been properly developed and documented. So this is important because software may have complex dependencies. Perhaps this component requires some other version of other components, and if you don't have a good configuration, you may run into many problems in the use stage. So that you should do a configuration review to make sure that everything has the right versions, and also documentations are complete and etc. So a complete delivery should include everything that can function correctly as soon as you install it. So evaluation is when the test engineer needs to evaluate the results by comparing the results with the goals outlined in the test plan and preparing metrics to determine the current quality of the software. So how do we know when to stop testing? So we can consider the testing completeness, the percentage of the test cases that have been run, and percentage of code that has been tested, and reliability based on trends in the testing error rate. So I think we ran out of time, so we'll continue our discussion next class.